Black holes, two words that evoke a sense of mystery and the unmatched power of the cosmos. Yet, deep within these enigmatic objects lies a crossroads, perhaps even a violent collision, between two of humanity's greatest scientific theories. Prepare to journey into the very heart of cosmic paradox. Have you ever wondered about the most fundamental forces shaping our universe? The laws that govern everything, from the graceful arcs of planets through space to the fall of an apple onto the grass below. The first of these is gravity, a force so familiar we feel it in every step, every leap, and every moment we remain anchored to the Earth. Gravity's invisible hand sculpts galaxies, steers the orbits of planets, and draws together the very fabric of the universe. But there is another realm, far beneath the scale of apples and planets, a world where rules turn strange and common sense dissolves. Welcome to quantum mechanics, the science of the ultrasmall. Here, atoms and subatomic particles dance to rules of probability and uncertainty, forming the building blocks of all matter. In this microscopic world, particles can be waves, and nothing is ever quite certain. These two great theories, Einstein's general relativity, ruler of the immense, and quantum mechanics, master of the minute, usually reign in separate domains. Yet, there exists a place where their influences converge and clash: the black hole. Here, mighty gravity and the unpredictability of the quantum realm face off, creating one of the greatest scientific mysteries of all time. When we try to use the mathematics of general relativity to explain the tiny, dense regions inside black holes, or apply the equations of quantum mechanics to the monstrous gravity of these objects, something astonishing happens. The numbers don't add up. The formulas clash. Theories that work so well on their own suddenly become adversaries, and a mathematical battle erupts, a conflict between the infinitely large and the infinitely small. This profound disagreement is why, even after decades of study, scientists still lack a single, unified way to fully describe black holes. Both gravity and quantum mechanics must be considered, but so far, no one has found the key that unlocks their secrets together. Despite this, our quest for understanding continues. At the very heart of our own Milky Way galaxy lies Sagittarius A, a supermassive black hole containing the mass of 4 million suns. Sagittarius A is a cosmic laboratory, and by watching the stars that orbit around it, scientists hope to unravel its mysteries. For years, astronomers have tracked the orbits of dozens of stars swirling around this dark heart. These celestial dances, measured with extraordinary precision, reveal crucial clues about the strength and nature of the black hole's gravitational grip. Some stars swing perilously close to the event horizon, the invisible boundary beyond which nothing, not even light, can escape. To put their proximity into perspective, these stars pass within just a few billion miles of the event horizon, a hair's breadth compared to the vastness of the galaxy. The dangers of these close encounters are immense, especially for stars with planets in tow. As they skim past the black hole, the intense gravitational forces can disrupt their orbits, flinging planets into new trajectories, or even tearing entire solar systems apart. Imagine, for a moment, a planet unlucky enough to be caught in this drama. A world pulled by the relentless gravity of the black hole, its fate sealed like a moth drawn to a flame. Ripped from its parent star, it spirals ever closer to the abyss, helpless against the inevitable. Picture another scenario: a distant alien civilization watching their beloved star, S2, trace its familiar arc across their sky. Suddenly, they notice a change. S2 begins to wander, drawing nearer to the galactic center, to Sagittarius A, into a region known as the tidal disruption radius. Within this boundary, the black hole's gravity becomes overwhelming. For S2 and any worlds that might orbit it, the end would be both spectacular and inescapable. But what if you, yourself, could fall into a black hole? Contrary to the dramatic scenes imagined in science fiction, crossing the event horizon would be eerily uneventful. No sudden jolt, no visible barrier, just a silent passage through an invisible one-way door. You would float gently across, feeling nothing unusual, even as the universe outside slips forever beyond your reach. If you could stand safely on a planet orbiting far from the black hole, the view would defy imagination. The sky would warp and twist, as the black hole's immense gravity bends the path of light itself. Distant stars would appear smeared and distorted, their images wrapped around the darkness like a cosmic funhouse mirror, and time would play tricks as well. To you, near the black hole, the universe outside would appear to race by at dizzying speed. Stars would be born and die, galaxies would collide and transform, all in the blink of an eye. Time for you would crawl, while outside, eons would pass in moments. Yet, as you drift ever closer to the singularity, the very center of the black hole, the experience would become far more extreme. The difference in gravitational pull between your head and your feet would stretch you out, pulling you into a long, thin strand in a process scientists call spaghettification. Rocks would be crushed to dust, and even atoms torn apart, as you're pulled inexorably toward the core. Here, at this ultimate boundary, gravity and the quantum world collide in the most dramatic way imaginable. Matter is compressed into a single, infinitely dense point, a singularity. This is a place where our understanding of physics completely breaks down, where the laws that govern the universe elsewhere simply cease to apply. A singularity defies comprehension. It is a point so small, so dense, that everything we know about space, time, and matter is thrown into chaos. It is both nothing and everything, a paradox that continues to baffle scientists and inspire dreamers. And so, the black hole remains one of the universe's greatest enigmas. A place where the rules of the cosmos are rewritten, where two mighty theories grapple for supremacy, and where, perhaps, the ultimate secrets of reality are waiting to be found. Is it not extraordinary, this meeting place of the immense and the minuscule, the known and the unknowable? The journey to understand black holes is far from over. Each new discovery brings us closer to uniting the laws of gravity and quantum mechanics, to unlocking the secrets of the singularity, and to understanding our place in the vast, mysterious universe. The adventure continues, with the promise that, one day, the darkness at the heart of the cosmos may finally reveal its light.